data scientist at Braintree in Chicago, and he's going to be presenting why you can't sit with us, understanding network analysis in Python with Mean Girls.
Great, thank you. And thanks everybody for helping me get set up. Live demos are always really fun, and they work out really well. So about me, my name is Richard Harris. I am a data scientist at Braintree. I've been doing that for about a year now. Braintree is a payments processing company. We're part of PayPal. Like every tech company in America, we're hiring. If you want to move to Chicago, please talk to me. We also have offices in San Francisco and a few other places. I've been doing data science for about a year there, 2 years in other roles, and then kind of a wide spread of other things before that. So this is a talk about network analysis and Mean Girls. Just as a caveat and an aside, we're using Mean Girls as an academic kind of discussion. It's a PG-13 movie, but it touches on race and gender and sex and orientation and all this kind of stuff. So just to say that I don't condone it, but we're talking about it as a kind of academic subject. So why does this matter? The best way I can show about why this matters, and here we get to try another live demo part, is this clip from the very beginning of the movie. So I apologize for if you can't hear it, let me know. But so it kind of goes like this.
Here, this map is going to be your guide to North Shore. Now, where you sit in the cafeteria is crucial because you got everybody there. You got your freshmen, ROTC guys, preps, JV jocks, Asian nerds, cool Asians, varsity jocks, unfriendly black hotties, girls who eat their feelings, girls who don't eat anything, desperate wannabes, burnouts, sexually active band geeks, the greatest people you will ever meet, and the worst. Beware of the plastic.
So yeah, so there's a lot of networks in Mean Girls. In fact, there's dozens, as we'll find out. And this matters because social network analysis kind of shows us, okay, let's not look at people individually and assume that their attributes, that the things that make them special are the only thing that affects what they do. Actually, the ties between people and the ties between groups really has a huge effect on what happens. So what we're going to do today is we're going to look through the basics of network analysis and introduce you to NetworkX. NetworkX is kind of the go-to library for network analysis in Python. It's not the only tool for it. There are better ones, but this is the best one in Python. We'll also use matplotlib to plot out a lot of these networks. So if you know matplotlib, it should be pretty easy to access it. If not, have fun. And kind of just some standard techniques and libraries from Python 2.7. This is all in 2.7. I don't know 3. I know I should know 3, but I don't yet. And then we're going to kind of apply it to Mean Girls. We're going to create the full network of what the actual Mean Girls movie looks like, and then kind of look at a couple of different cases about how you've probably been personally assaulted by Regina George before, and why you can't sit with us. We've got a couple of other extra ones that if we have time, we'll get to. If we don't, I promise you, you're missing out on something really cool. So okay, so Mean Girls. It's this movie, it comes out in 2004, Tina Fey directs it, it's based off a book, it's really funny. I had this whole slide about trying to explain the story of Mean Girls. I'm not gonna do that. It's painfully awkward and I'm not gonna put you all through that, but I'll talk about the data. So the data we use is all the lines that are spoken in the film. And we draw lines or connections or edges between two characters if they speak directly to each other. This means that voiceovers, speaking to a group, musical numbers, cases where it's not clear who's talking to who, we just code it with the speaker. So cases where like Cady is up just voicing over everything, she doesn't really talk to anybody at that point. And I collected all this data by hand by watching the movie over and over and over again. I'm kind of sick of Mean Girls at this point, but so yeah, and this is kind of a point about how hard it is to find data, because network analysis is a very special kind of data. Not a lot of it is readily available. So quick introduction to it, it's kind of based off of two things. We have nodes and we have edges. So nodes are the things that we're connecting. So they could be two people, they could be two locations, they could be genes, in the body or diseases, they could be websites. The key point here is that there's at least two of them and that they can have some sort of meaningful connection between them. So nodes can also have attributes. So here I've just kind of like put together some dots, they're connected by lines, and they have different colors. So some of them are blue, some of them are red, some of them are green. Those are attributes. You can access them and use really cool analytics with them later. Edges are any connection between these two nodes. So there's a tuple. Node 1 is connected to node 2. And actually, nodes can have any number of edges, and there can be any number of edges at all. So node 1 could connect to node 2 and node 3. Node 2 could connect to node 1 and node 3, et cetera. And if you connect all those nodes together, you, of course, get a triangle, which is very cool. So edges can also have attributes. So here, I've just kind of made these edges bigger and smaller due to random numbers, but they can actually be meaningful, and we'll see them be meaningful in the future. So there's two types of graphs in network analysis. There's an undirected type of network and a directed type of network. Undirected networks are pretty simple. The order of the pairing of nodes doesn't really matter. So if you connect node 1 and node 2, that's the exact same thing as connecting node 2 and node 1. And there's kind of cool little mathematical thing where you can pretty quickly figure out how many maximum number of edges you can have. So here we have 3 nodes. 3 times n minus 1, which is 2, is 6. 6 divided by 2 is 3, and voila, we only have 3 edges. Because it's a triangle, and you can only have 3 sides on that shape. So directed graphs are a little more complicated. The order of the pairing does matter. That's kind of the key difference, which is to say that node 1 going to node 2 is different than node 2 going to node 1. Both of those things might happen. One of those things might happen, or neither of them might happen. And so this is kind of like a little example of like what my email inbox might look like. You have Google and Amazon kind of on the facing downwards and the facing right way. And those little rectangles are the points of the arrows. So they send me a lot of email. I don't send them any email at all. My work friends and I, my friends up at the top, sure, we all send each other email. We all go back and forth. And over here's my family. So mom and dad are talking to each other. Mom, dad, and grandma are all talking to each other. We're all talking to each other. Here's that really creepy, awkward cousin that you never want to reply to. He's sending you chain emails and that sort of stuff. And you can see that, because he's sending all of his stuff outwards, and we're not really sending anything back to him. So the directionality and the kind of in and out degrees of this really can show you some more of the dynamics behind that network. So how do we analyze these networks? Well, there's a few key features. One of them is centrality, and that is who's the most important part of this network. And there's actually a few different ways to measure that. You can have degree centrality, closeness, betweenness. We'll get into that in a second. Is the network connected or not? That is, do we have like one big network, or do we have a bunch of smaller networks that aren't connected? And are there brokers? Brokers are these kind of really cool individuals that sit between 2 different networks and really connect people together. So we'll go through degree centrality, which is really how many nodes are directly connected to you. So this is kind of like the 7 main characters in the movie, right? You have like Janice and Damien over here, who are the kind of like gothy, outcasty kids. Cady over here, who's off to she's the main character. You have the love interest here, and the plastics, the 3 blonde, terrible, kind of evil people in the movie. So we can find out, so there's something called degree. And degree is basically how many people are connected to you directly. And let me know if you can't read the numbers. They're probably a little small. But basically, so you have Cady over here. She's got 6 degrees. And that is 1, 2, 3, 4, 5, 6. She's connected to everybody. This is the same thing behind 6 degrees to Kevin Bacon. Here it's 6 degrees to Cady Heron. So Janice and Damien over here, they only have 2. They're directly connected to Cady and each other, nobody else. The plastics are all kind of 3, except for the exception of Regina. So it's pretty easy to understand. And we can normalize this by saying, all right, take the number of things that you're directly connected to and divide it by the number of things you could possibly be directly connected to. So Cady's got a 1, because she's got 6, and she can be directly connected to 6 nodes. Easy. Everybody else is kind of somewhere on the range between 0 and 1. In and out degree centrality is kind of the same thing, except this is with directed networks. In degree is how many people are pointing towards you. How many are like sending you things? And out degree is how many are you sending to other people. So I just randomly assign some directions here. Doesn't actually mean anything. Doesn't show up in the movie. This is just for display. If we look at the in degree one, Cady over here is 0, because she is sending something out to everybody else, and nobody is sending stuff into her. Versus Regina over here, who has 3. Cady's sending her something, Karen is sending her something, and Gretchen is sending her something. And you can do the same thing with out degree, which is just how much are you sending out. Here, Cady is 6, because she's sending it out to everybody else in the network, and Regina's only 1. She's only sending 1 over here to Aaron. So closeness centrality is kind of, it's a little different. It says like, okay, I don't care how many people I'm directly connected to. I want to know on average, how many hops does it take to get to me? So here, Cady is again 1. And we can kind of show this by going through and just really quickly calculating this out. So there's 1 hop there, 1 hop there, and there, and there, and throughout the rest of them. So out of 6 possible shortest paths, which are like of length 1, we had 6. Really easy. Here's Regina's closeness centrality. She doesn't have 1. So she goes, that's 1 hop, then a second hop, third hop, 4 hop. At this point, it's 1, 1, 1, 1. Now what happens when we go to the next person line? Here it's a hop of 2. She's got to go through Cady to get to Damien. So that's 2 hops. So instead of being 1 plus 1 plus 1 plus 1 plus 1, it's actually plus 2. And we see it again with Janice. So we end up with 6 over 8, or 0.75. So she's a little less close in this network than Cady is. Between the centrality is a little bit more complicated, but basically says, like, take all the nodes out there, find all the paths between those 2 nodes that are the shortest, and then find out how many of those go through the node that we're looking at. So here, almost everybody else is 0. Cady is 0.6, and Regina is 0.06. And why is that happening? So all the other nodes in this network have a short path that goes through Cady, or they don't go through it at all. You know, these 2 can be directly connected with 1 hop, but Damien's shortest path to anybody else over here goes through Cady. Versus Regina, for the most part, everybody can get to her directly or through Cady. But if Gretchen wants to go say hi to Aaron, she's got to go through Regina first. So this kind of shows more who's connecting groups of people that otherwise aren't connected. Speaking of connections, here's connectedness. So we kind of have a couple of terms here. A connected network is one where all the nodes in this network are connected. And an unconnected one is one where they are not. That's pretty easy to understand. Number of components is how many subnetworks there are. If they're all connected, there's only 1. If they're not, there's more than 1. And the largest connected component is you take the largest subnetwork and you just give me the number of nodes in it. So this is a connected network. And in fact, it's connected, it has 1 component, and it has 7 nodes in it. Versus an unconnected network where we've kind of just taken out like Cady's relationship here and just stuck her in there. This is unconnected. And in fact, it's got 3 components, and the largest one has 4 nodes. So this is kind of a way to like look at the overall health of a network. Is it connected? Are people like talking to each other, or is it not? Finally, brokers, they connect these disparate groups in the network. Cady, in this case, really is a broker for this one specific 7-node network. And we kind of identify them by having a high between the centrality, or if we remove them from the network, the number of components kind of increases. So the networks kind of break apart without them. So here they are kind of in this normal state. We take, oh, I didn't put that other slide in there. Anyway, if we took Cady out of here, all of a sudden we would have a bunch of different subnetworks. Okay, so let's apply this to stuff. So we're going to start with we're going to start by going through, and let me know if you can't see the text. So we're going to just import NetworkX as NX, add some like matplotlib stuff, and we're going to look at one scene in the video that's really kind of quick and easy to understand and really shows a lot of what's going on. So,
are these notebooks available?
Not yet.
And he's with Taylor Waddell. I heard they're going out.
Wait, Jason's not going out with Taylor. No, he cannot blow you off like that. He's such a little skis. Give me your phone.
You're not gonna call him, right?
Do you think I'm an idiot?
No.
Waddell on South Boulevard?
Caller ID.
Not when you connect some information. Hello? Hello, may I please speak to Taylor Waddell?
She's not home yet. Who's calling?
Oh, this is Susan from Planned Parenthood. I have her test results. If you could have her give me a call as soon as she can. It's urgent. Thank you. She's not going out with anyone. Okay, that was so fetch.
So this is a great example of network analysis because without kind of the system of the network that already existed, Regina George would never call Tyler Waddell's mom, and this poor suburban lady wouldn't faint. It's fantastic. So let's kind of map this out. So what we need to do is pass in a list of nodes. So here's a list. It's called list of characters, and it kind of has the 7 or so nodes in there. And we'll put in the interactions. So NetworkX expects like a list of tuples. In this case, it's just sender and receiver. Cady to Regina, Cady to Gretchen. This is people who've been talking to each other or are in the scene. And then we kind of create a graph object, so nx.graph. And we pass in the nodes using the add nodes from method and the edges from the add edges from method. We can kind of see what the information of this graph looks like. And we've got 7 nodes, 10 edges, and on average, people are connected to 2.85 other people. So that's kind of doable. So let's look at this. We can print this out. This is the circular layout thing. Just kind of says like, here's where in 2-dimensional space I want the nodes to be laid out. There's a few functions in here. NetworkX doesn't do a lot of really good ones. So we're kind of hamstrung there. And then we just say, like, OK, go through, make them really big, make them blue, make the lines gray, and add labels. And if we do that, this is kind of what this all looks like. You know, the plastics are over here, all kind of talking to each other. And Gretchen makes this called Jason, or Gretchen is interested in Jason, and Regina makes this called Mrs. Waddell, who then calls Taylor. So that's kind of what this looks like. We can actually kind of change this layout a little bit. Yeah. Her father invented toaster strudel. So if we change how this is laid out, you kind of like actually see what this really ends up being, which is a really tight cluster of people over here and a group of otherwise unconnected people over there. So we can kind of see, we can ask NX, NetworkX, okay, what's the number of degrees here? It's pretty easy to figure out. And we can find the degree centrality, which is just normalizing it again from 0 to 1. And sure enough, Gretchen is pretty big and Regina's pretty big. And it turns out that with such a small network, with the other measures of centrality, that still holds. So they still have pretty high closeness centrality, though most everybody does, and they have pretty high betweenness centrality. We can even see, like, okay, is this network connected? NX dot is connected, yep. What are the number of connected components? There's one, because it's a connected network. And there's no isolates. Isolates are nodes that don't have any connections to anybody. So let's move back about 30 seconds before Regina George, who's the girl on the phone, actually makes this call. So we'll just go create a new network and just take her out of that interaction. And we have one less edge, and we have a smaller degrees. And if we draw that out, all of a sudden this looks really different. This big connection here between these two is gone. And the only thing that matters right here is this one. And we're going to see that, Gretchen becomes much more central. So any one of these three ways will tell you, yep, Gretchen's got a 0.66 here, 0.66 there, 0.6 there. She's all of a sudden really, really important. In fact, she's the one person who connects these three and these four. So what happens if we just take her out of the picture completely? Like, how would this even work if she wasn't even part of this graph? Well, we take her out. It's a much smaller graph. And if we graph that, all of a sudden they're unconnected. And without this connection here between, well, where Gretchen should be and Jason, Regina George has no reason to go bother Mrs. Waddell. And all of a sudden everybody's safe and happy and doing really well in Old Orchard Mall. Incidentally, Mean Girls takes place outside of Chicago, so there's another reason why I picked it. So let's kind of look at the full network now. So we do the same thing. We import NetworkX, matplotlib. I import CSV. So I have all the nodes and the edges from the entire set of the movie data into CSVs, and I just import them. Here it's a list of tuples for the nodes, and we have like an identifier. Here it's 0, and an attribute. In this case, the name of the person or Cady's dad. The edges, again, are just this kind of big list of tuples between these keys and these other keys. So we'll set up another graph object. We'll look at the info. It's much bigger. It's got 82 nodes. It's got 96 edges, and just over, on average, 2 direct connections on any given node. So we can just do nx.draw, which will just plot out the most ugliest graph ever. But this is good to kind of see what it looks like. And here we go. That's Mean Girls in a nutshell. Thank you. No. But you do kind of see some, there's a big central network in here and a bunch of smaller networks outside of it, which if you've ever been to high school, that pretty much sums up high school right there. So is this network connected? It is not connected. It's got 20 different subnetworks. And we'll find out that a lot of these are isolates. And in fact, it turns out that of them are isolates, in fact. So this is just going through, so nodes iter just basically says, like, OK, send me through all the nodes of Mean Girls one by one. And if they're in this list of isolates, let's print what they look like. And these are like some of the extras, right? Girl 1, girl 8, homeschooled boy 3, probably not super important people. We could remove them. So it's pretty easy to go ahead and remove like isolates. And yeah, I mean, the number of nodes goes down. This top one is the world without these isolates. And if we draw it, it doesn't really look that different. In fact, it looks almost exactly the same, just a little less people around the circle. But we'll use the full data set because that's kind of more authentic. So we got some characters that we're interested in, right? We know that we're interested in like these main characters. We can find out which node they're attached to. So Damien is node 21, Cady is node 2. This is kind of in order of when they speak in the movie. And we can figure out what the degree centrality is for these people. And unsurprisingly, Cady, who's the main character of the movie, blows people out of the water. She's directly connected to 25 people. If we look at closeness, that's that kind of what's the average short path to a given node? She's still pretty big, but actually most people are. So what this might tell us is that they're probably all part of this big network, and they're all probably pretty closely connected to each other. But here's the interesting part. If we hop over to between the centrality, Cady blows everyone else out of the water with 0.27. Everybody else is kind of around 0.01. And what this tells you is that Cady is playing this broker role. She's kind of sitting between a bunch of these different networks and connecting them, which is a really cool part. There's a lot of power in connecting different groups. There's also a lot of danger in it. If you've ever seen the movie, she kind of goes off the deep end, and like a lot of bad things happen to her because of her role as a broker. So we're going to kind of set up a bunch of different dictionaries here that just say, like, here are some different groups of people we're interested in. Cady, her friends, the plastics, some of the love interests, the teachers, and like the family members. And this just goes ahead and sets up a dictionary with those values in there. And we'll set up a big dictionary that just says, like, all right, I want Cady in any graph to be really big, blue, and I want to be able to label her name. And so we can go ahead and draw this. And if we draw this out, this is just the nodes. So this looks a little different. Like, we have a lot of little tiny nodes that don't really matter and some bigger nodes that do matter. But we kind of want to figure out like what their names are. So draw NetworkX labels will actually label each node with like a given name. And we kind of pass in this dictionary generator of what those different names are. And this is okay. It's kind of bad. It's hard to read. So let's take out all the ones that are for the smaller characters. Makes it a little bit better. And this just basically says, like, okay, in that big dictionary, if label is true, go ahead and draw those labels. If not, don't worry about it. And let's go ahead and like just change blank spaces into line breaks. All right, that's a little better. Like, you can actually kind of read that. I don't know how you people in the back can read it, but it's semi-legible. We can add in the edges, and that looks terrible. That looks awful. We don't want that. So we can change some of the attributes in the edges one. Here we're going to make it kind of like translucent, and we're going to make these lines gray. That's a little better, but we kind of want to see how often people are talking to each other. We don't know if these lines are like they have one line exchanged in the movie, or if they have 50, 100, 1,000 lines. So we'll go ahead and we'll kind of do this this counter from collections, which will set up a dictionary where each key is this interaction, and then the value is how many times. So here, I know this because I took down all this data, Janice and Cady speak 62 times in the movie. And we'll kind of pass in a weighted age list, or edge list, which basically says, like, okay, NetworkX, the third item in this tuple is going to be the weight of this interaction. 1 is smaller, 62 is much bigger. And we're going to kind of set this up. This is just to make this look pretty. And if we go ahead and draw that out, all right, doesn't look great. They're all kind of clustered in here. Something's wrong with our layout. We can kind of see that some of the lines are bigger or thinner over here. And if you could see it behind the nodes, you'd see that these lines are thicker where there's more interaction. So let's change out some of these layouts. So there's a circular layout, which looks like this. This is all changing this pause value up here. And what this layout does is it arranges everybody in a circle and just draws the lines between them. So we can kind of see that, Regina George and Cady are pretty deeply connected. They talk a lot. But, this isn't really helpful. It kind of doesn't show us clusters of activity. It just says, like, people on this side go to the other side. We can also do this on a random layout, which also isn't really helpful. It's just kind of chaotic and doesn't really show much semantically. So let's go ahead and use the spring layout again. The spring layout kind of says, put more tightly clustered people together in the center, and then put less connected people out to the sides. And we'll add this like spring coefficient, the 0.35, to say, like, we want a little bit of space, even if they're deeply clustered. And we kind of get something like this. And this is actually pretty legible. It's not perfect, but we can kind of see, here's Cady and her parents over here. The plastics are over here, kind of love interests off to the side. And and then Damien and Janice, who are Cady's best friends, kind of over here. Everyone's kind of clustered, but they're clustered in different directions. Now, NetworkX will tell you if you go to their documentation that their labeling is not great, and they really don't draw very well for these big networks. So if you can export this as a .graphml file, as a .gephi file. There are 3 or 4 different programs out there that will do much better visualizations of your data. Gephi is kind of the one I know best. It's open source and is in Java, and it's not super great, but it works. Okay, so let's kind of look at some more stuff. So here, this is kind of these two like corner cases. This is us actually using network analysis to find out something. And the first thing we might want to find out is who actually has been victimized by Regina George. And this is one of the bigger scenes.
Can I just say that we don't have a click problem at this school, and some of us shouldn't have to take this workshop because some of us are just victims in the situation? That's probably true. How many of you have ever felt personally victimized by Regina George?
So if you're not familiar with the movie, the Plastics had this book, the Burn Book. And the Burn Book, they take pictures of all their classmates, and they write really terrible things about it. And Cady has spent most of this movie trying to destroy the plastics, essentially. And the Burn Book gets out. There's a huge fight in the hallways. Everybody is wailing on each other. And they shuttle all the girls into the gymnasium to talk about it. And Regina George, of course, is the head plastic here. So yeah, the movie says you've probably been victimized by Regina George. Is that the case? Well, we can figure that out. We actually can. We can show this. So this is the network from before. It looks a little different because when you run the algorithm again, it puts them in different places. But more or less, people are connected, but we can actually figure this out. So let's look. So this node connected component kind of gives you how many nodes are ultimately connected to, in this case, Regina George. 31 is her node key. And this will basically say, I don't care if it's 1 hop, I don't care if it's 10 hops. Just give me every single one that happens. And 56. So she's connected in some way to 56 other characters in the movie. And that actually is just under 70% of every character in the movie. And this includes flashbacks, this includes extras. She kind of touches everybody. And we can kind of print out, this cutoff equals 1 says, give me everything that's 1 hop away. So there's a few characters that she's directly connected to. And a lot more that she's either 1 or 2 degrees from. And even more that she is 3 degrees or less from. So if you've ever played 6 Degrees of Kevin Bacon, you know that once you get to 3 or 4 degrees, you're probably at Kevin Bacon or you're almost there. So 3 degrees is a lot in a network. So we're going to go ahead and just set up a list with all the 1 hops, all the 2 hops, and all the 3 hops. And because in NetworkX you can't pass in a big tuple of, I want to go from node, Cady to Damien to this person to that person, you actually have to do 3 different hops. This just says okay, I'm going to do each of those different hops as a entry in this list. And we kind of end up with this big, big old list of 31 to 10, 10 to 21, 21 to 28. And so let's draw this out. And what we're going to do is anything that's 3 hops away, we're going to color out yellow. Anything that is 2 hops away, we'll color out orange. And if you're in the danger zone, we'll color you red. You're 1 hop away. And we can draw that out. Yeah, you've probably been victimized by Regina George. There's almost nobody in the network she hasn't touched, and even if she hasn't touched you directly, you're probably connected to somebody who has. And this kind of talks to networks also are methods of transmission, right? You can track the spread of viruses with networks, you can track the spread of violence with networks, and this is a way to show that. Regina George has no real connection to this node over here, whoever that is, but she knows somebody who knows somebody who knows somebody, and Regina's actions probably hurt that person as well. So my final little example, because I'm, I think, 5 minutes out, is why you can't sit with us. And so this is kind of it was a sexy hook for a question that actually is answered in the movie. So I'll just run this real quick.
Gina, we have to talk to you. Is butter a carb?
Yes. Gina, you're wearing sweatpants. It's Monday.
So? So that's against the rules, and you can't sit with us. Whatever. Those rules aren't real. They were real that day I wore a vest, because that vest was disgusting. You can't sit with us! These sweatpants
pants are all that fits me right now. Fine. You can walk home, bitches. That's where you're going, fat ass.
So networks have effects. Subnetworks have even more effects. And I can go into this whole sociological discussion about, group dynamics and rules and whatnot, but the ultimate point of this talk is that networks matter, and networks matter because your network influences you just as much as you influence your network. What I'm going to show here is just how much of an effect Cady has over the entire movie. So if you're not familiar with that scene, Cady falls in love with this guy named Aaron. He's the teenage throb heart in this thing. And at the Halloween party, Regina George makes out with him instead, and Cady decides she's going to enact revenge on the plastics. And she does. She ends up getting Regina these Swedish protein bars that just make her, still look very nice, but enough weight that she has to wear sweatpants. And what's really interesting about this scene is that Cady never says, get out. Cady never says, get out of the network, I don't want to see you anymore. She never takes direct action. Her actions go through all the different parts of these networks to get there. So we can kind of show you just how much influence she wields. So we'll draw out this graph again. This is the one we've seen a few times before. And that's just the whole network of here. And let's take Cady out of the network. Let's just pretend that this whole movie happened without Cady in it. And we can just kind of go through here. We'll remove out all the edges that she's a part of. We'll take her out of the nodes. And we'll just kind of get rid of her completely. Now, without her, that same network looks kind of like this, which it's not super different. I think some of the lines are a little messed up, but so it's not super different. Like the nodes they're still kind of a centered group of people here in the network, but a lot of them aren't that much connected anymore. And in fact, if we print that out, there's a fewer average degree, there's fewer edges, and we have 30 unconnected components versus 20 before. And if you look at this is just kind of all the different subnetworks there are. Here's one. Here's the main one, which is real long. And then everything else are these subnetworks, either isolates or kind of triads or dyads. And let's go ahead and just graph what that looks like. What this is going to look like is for Cady, let's go ahead and color each subnetwork a different color in the node. And if they're part of this main network, let's make the nodes really big. And if they're not, let's make them really small. And so in the world without Cady, there's a big network that involves people being connected kind of tertiarily to this one in the center, but there's a whole bunch of other small ones that just aren't. So you can kind of see them hanging out here around the edges. And if we do that again for the real world in the movie where Cady exists, we've got more. A lot more of them are connected in there. But this doesn't really tell the full story, right? And we can tell you, we know there's a much bigger number of smaller networks in the no Cady world. This doesn't really tell you how tightly connected these networks are, right? Like this guy over here might be the same shape as this one over here just because they've had one interaction throughout the entire movie. So let's kind of change the size of these nodes based on what the average shortest path is. So if you're in this kind of tight cluster in the middle, you should be bigger, and if you're not, you should be much more small. So this is for the world without Cady. And that's different, right? You've got some really big players here, a lot of people who are part of the network, but they're further away. And in the world where Cady exists, this is what it ends up being. Everyone's kind of part of the same network, but she's huge. She's a huge player in here. And what this really comes down to saying is, Cady's a broker, and brokers are, the subtitle of this talk really should be, Cady's a broker for good and evil, because here she is in the middle. She connects a lot of people, which is good. If you see the end of the movie, there's this whole redemption scene where she says, I'm sorry, we all love each other. He's part of my spring dance crown thing, and we're all friends now. So being a broker can be really good. She has a lot of influence here. But because she's part of this network, she can also wreak havoc on people's lives without ever actually doing anything. So throughout the movie, she breaks friendships apart. She gets people kicked out of networks. She, all these different things. And she can do it not because she's actually doing it, but because she is part of a network. And her influence there is incredibly powerful. So the reason why You Can't Sit With Us is such an important thing is that we're saying, okay, why You Can't Sit With Me isn't so powerful. You Can't Sit With All of Us is really important. And you can't really measure that without hopping into this world of social network analysis. So that's kind of why You Can't Sit With Us. I'm just on time for the money. So I'll end it there, and thank you so much. Yes.
I want to know who gave Glen Coco 4 candy grams.
Okay. Let's get some other questions in first, and if we have time afterwards, it's a 2-minute spiel, but I think it's actually really interesting. I had to cut it for time, but if there aren't any other questions, we'll go into it. So everyone else ask your questions first, and we'll end on that note.
Does NetworkX have multi-edge graphs?
Yes, it does. It's actually really recent that they added it, but yeah. So you can set up a multi-graph. You can also set up a multi-graph here in this case means two nodes can have different edges. So you can also like go node 1 to node 2, and then a separate node 1 to node 2 edge. I don't know how to use it very well, but they do have that capability, yeah.
Does NetworkX play well with more traditional databases? Like, for instance, if you had a bunch of data in a Postgres database, could you query it and run it through NetworkX and see some results?
Yeah, so NetworkX doesn't work super well with huge databases. There are some other libraries, or Gephi is a good example, that work well with that. But really, I mean, if we go back to what the data looks like, it's just, this one connected to that one and a list of nodes. So if you can query your database in a way that pulls it out, yeah, it should be pretty easy to do it. Now, the caveat about data is that a lot of data isn't stored in a way that makes making edges very easy. Nodes we can find really easily, right? Like any sort of like statistical analysis is generally like person 1, person 2, person 3, person 4. We don't have all the connections between person 1 and all of the other people. And that also means that in some cases, network analysis can be a little bit more biased because if you don't know what you're missing out of these connections.
Is there a way to have the graph print itself out as it evolves over time? So like throughout the movie, having the graph print out based on who's talking, not necessarily at the same, at that instance, but just like a GIF.
Kind of as new connections kind of come in. Yeah, so there is, and when I took down this data, I actually did kind of keep a track of what scene happened. I didn't get the chance to run through that, but it's definitely doable. You could either just have it print out, okay, here's scene 1, here's the new connections, here's scene 2, here's the new ones, and just kind of loop through that. Or if you go into something like Gephi, which is this open source network visualizer, they probably also have that capability. If they don't, I don't know for sure. I don't play with Gephi that much.
I was just going to ask, where can we find you online?
That's a good question. I haven't actually set up any sort of online presence. I do have a GitHub that I set up for this that I didn't fill out. I think it's this one. Nope, that is not me. What did I name? What did I do that as? There we go. Okay, Richard Jonathan Harris, 2 O's, no A's, or well, an A in the middle. I haven't actually put anything up there yet, but I will at some point. I'm hoping to get a blog set up. I have tried to avoid having an online presence, but this is the world of everyone has blogs and Twitter accounts and stuff. So keep an eye on that. I will probably try to put all this stuff up there at some point in the next couple of weeks. And that's Jonathan. I'm sure Richard J. Harris is very nice, but I don't know who he is.
Could you describe what sort of analysis you do for huge networks that you can't visually plot?
So there's a few things you can do. There's kind of levels of like basic centrality and that sort of thing. I actually don't do that much network analysis at scale. The things I have been involved in is there's a great guy. Let me see if I can find his website. I'm gonna Here he is. So this is Andy Papachristos. He's a sociologist out of Yale, and I've helped work with him. His whole thing is looking at crime networks in Chicago. And the way that he does this is he goes and says, like, all right, give me all the arrest records in Chicago, and then if you get arrested at the same time together, I'm going to draw a line between you. Maybe you're friends, maybe you're foes, whatever, and it ends up being this huge network of literally millions of people and tens of millions of edges. And what he does is he goes through and says, like, okay, we can identify who has been killed by violence in this network. And we can identify who has been picked up with a gun illegally in this network. And so let's take kind of the percentage of everybody within 1 hop, and then 2 hops, and then 3 hops, and then say, okay, if 90% of the people you've been arrested with have also been arrested at some point with guns, your likelihood of being victimized by violence goes up by X amount. And then you can actually take that into just like your regular Bayesian analysis or statistical analysis and throw that in as actual variables. Because then you're taking it back into a world where you have 1 observation per row. So that's kind of like one way you could go about it. If you are interested in really cool applications of network analysis, this is the guy to talk to because he has some really cool work he's done. Anybody else? All right, let's show you who sent Glen Coco candygrams. All right. So for those of you who don't know, this comes out of this scene. Kind of the awesome.
Candy cane girls. Okay, hurry up. Taylor Zimmerman, 2 for you. Glen Coco, 4 for you, Glen Coco. You go, Glen Coco. And Cady Heron. Do we have a Cady Heron here?
It's Cady.
Oh, Cady, here you go. 1 for you. And none for Gretchen Wieners. Bye.
So, for those of you who don't know this scene, this is part of Cady's Revenge in the Plastics. And every year, Regina, who's the queen bee of these, sends everyone in the Plastics these candygrams. And it's the kind of high school thing. So Cady goes ahead and says, like, all right, because her friend Damien is the one who's in the Santa Claus outfit, let's just throw those in the trash, and let's send some out to everybody but Gretchen. And of course, Gretchen starts kind of going crazy, because what am I at the network? Am I in? Am I part of this group or not? But there's also this little scene of Glen Coco. Glen Coco is played by some early 2000s actor. Apparently it was a big deal that he had a cameo. But we can kind of identify him. Here he is, there's his node. And we can modify our network code a little bit just to show him out. And so what this is going to do is it's going to say, like, all right, if you are Glen Coco, so here's a normal network. And here we're going to say, like, okay, if you're Glen Coco, I want you to be huge, I want you to be 10,000 points, and I want you to be bright yellow so we can find you. And there he is. There's Glen Coco. He's kind of over here. So we can go through. We can figure out, he's got 1 degree. He's connected to 1 other person. And we can find out all the different shortest paths to him. They're pretty long. And we can kind of visualize this. I think this is the one that visualizes it. Yeah. So we can visualize that. And here's everybody that's got, I think 2 or 3 hops away from him. So Glen Coco kind of connects over here to Damien, who then connects off to a few other people. So let's find out who's connected on that path of 49, which is Glen Coco, to 21, which is Damien. If we do that, there's only a few candidates here. Okay, so we're getting somewhere. And we can actually print out who those people are. And there's a few different people who are here. The girl who doesn't go here is the girl at the end who, if you haven't seen it, she just doesn't even go here. They call her out on it. So we're going to make some assumptions, right? We're going to assume that teachers probably aren't sending Glen Coco candygrams. That would be in a morally gray area. The girl who doesn't go to school there probably isn't doing it because she doesn't go to school there. And any of the main characters we're going to assume probably aren't doing it either because we'd see them doing it on camera. And finally, I'm going to make one other assumption that, Glen Coco is straight and that there are girls sending him candygrams and that he is sending, could not be right, but we'll make an assumption for goodness' sake. And it actually comes down to 3 people. So it's this 48, this 28, and this 50, who we know are Taylor Zimmerman, Trang Pak, and 28. Oh, and Short Girl. Name someone Short Girl. And so we can draw this out. And so probably probably, these are some of the people who sent him candygrams. Now again, because we only have like spoken interactions on film, this speaks to the kind of biasness of networks. We don't have the data, so we don't know if there are other connections. But probably my guess would be one of these 3 or 4 people are some of the people sending him candygrams. So, good job. You go, Glen Coco. Thank you.